words. Okay, so what I would like to talk about is to very quickly introduce contact structures and how to construct contact structures. So this will be sort of, if you remember John's equivalence, he was talking about open books, and I will just give you some ideas what on the other side, what structures he considered on the other side. And I would like to give you a way to construct lots of these structures, and then towards the third and fourth lecture, how to actually gain some information about them using the theory Peter and Zoltan are talking about. So how to apply Heegaard Floer theory and these homologies to understand context structures better. And so today I mainly will focus on some definitions, and maybe we will conclude with a theorem which I will plan to prove next time. So let me just begin with the very basic definitions. So I have to ask my contact topologist friends to excuse me, because we will start from scratch. So let me just try to begin with the definition. So first of all, Y is always a closed-oriented three-manifold. So Y closed-oriented. I will stick to Y instead of M, as John was saying, because it's easier to remember. Y is a three-manifold because it has a point where, three guys are coming up, as opposed to X, which will always correspond to a four-manifold. And I would like to make the point that somehow orientation doesn't seem to be such an important issue, but whenever you do gauge theory or you apply these theories, somehow the orientation is a really crucial part of the data. So I will try to make an effort to point out where we use it and how we use it. So let's say that Y is an oriented closed three-manifold, and let's take a one form on Y, and we say that it is a contact one form if alpha wedge d alpha is actually positive. So here we immediately use the orientation of the manifold. We could just require alpha wedge d alpha to be non-zero, but we strictly say that it should be positive with respect to the orientation. Okay, and the next definition is that Xi, a two-plane field, is a contact structure if there is a contact one form alpha such that the kernel of this one form is exactly Xi. Now, before going any further, I would like to point out that somehow when we choose such an alpha, we actually get some more information. In fact, we get also an orientation for Xi. So notice that alpha also orients Xi, since we can extend V, a vector transfers to Xi with alpha V equals 1 to an oriented basis. So we just take a vector which is sort of transversal to Xi, and we declare this to be the first basis element of a basis, and this gives an orientation for Xi. So from now on, we will always consider such oriented two-plane fields which are given by this equation, and this is what I will call a contact structure. The usual definition requires the word co-oriented contact structure, and I will always assume that this is fixed. So this is sort of, again, a piece of data which is related to orientation, and this will be very important later on. Okay. So the motivating problem of the subject, as John pointed out, contact geometry somehow has different flavors. There is a sort of a topological and more analytic flavor. When you are working with the forms themselves, this requires lots of analysis. When the practice tells that if you are only concentrating on Xi, on the contact structure, this can be understood in more topological terms. So we would like to focus on the topological side of the story. And so the motivating problem is somehow understand all context structures on a given three-manifold Y. Of course, understand, we have to put in, it's a very undefined problem. What we would like to have is a complete list of context structures which can live on Y. And there is a suitable equivalence relation, namely when the two context structures are isotopic, which means that the two plane fields are homotopic through two plane fields which are context structures themselves. So this is what we would like to sort of understand, and this is only a motivating problem. We will not get a complete solution in general, but as you will see, in many nice cases, we can actually get some reasonable answer. But as practice tells, context structures are not created equal. There are sort of context structures which are easy to handle and ones which are harder. So this is the content of the next definition. So we say that a disk in a contact three-manifold. From now on, I will record the three-manifold and the fixed two-plane field, the fixed context structure in it. And we say that a disk, a two-dimensional embedded disk, is over-twisted, and I will just write OT for that. So it's an over-twisted disk if psi is tangent to D along its boundary. So if you have some memories about how to integrate a two-plane field, somehow this assumption is just the assumption to say that the two-plane field is not integrable. So we cannot expect a whole surface to be tangent to psi, but we require this to happen only along the boundary circle. If we have such a thing, we just call the context structure over-twisted. The definition is sort of unclear. Why shall we study them separately? But I will give you a theorem without any kind of indication how to prove it, which might explain the importance of these. And so the definition is that Y psi is over-twisted if it contains an over-twisted disk. And if a context structure is not over-twisted, it is called tight. So otherwise, Y psi is tight. So probably this is the most important definition of the subject from the topological point of view. And there is a fourth piece of the definition, a symplectic four-manifold symplectic and compact four-manifold X omega is compatible with a given context three-manifold Y psi if Y is the boundary of this three-manifold and omega restricted to psi is non-zero. So remember, a symplectic structure in a four-manifold is just a two-form which is closed and non-degenerate, meaning that omega wedge omega is non-zero. Since it is non-zero, it already provides an orientation for X. And in this line, we require that the orientation given by omega and on X and the orientation of Y given by the contact form alpha should match up. There is also a terminology. In this case, Y psi is also called fillable or more precisely, it is called weakly fillable. And X omega is called the weak filling of it. I would like to make the point that X should be compact. If you relax the compactness assumption, then it's not so hard to find an X omega with these properties when you allow non-compactness. Okay, so these are the definitions for a while, and now comes the two theorems which sort of, the one which I just promised, which explains the special treatment for over-twisted contact structures, and this is a theorem of Eliashberg, which just says that over-twisted structures are not that interesting after all. And it reads as follows. So suppose that Y is a fixed, closed, oriented free manifold, then the following is true. If Xi1, Xi2 contact structures are homotopic as two-plane fields, then they are isotopic. So the essence of the theorem is that if you can move one contact structure into another and both are over-twisted, then actually you can do it through contact structures. And the second part is that for any two-plane field, I did forget the over-twisted, right. Thank you. Yeah, otherwise it's sort of not exactly true. That would be the whole point, right? To study the rest. Thank you. For any two-plane field, there is an over-twisted contact structure homotopic to it. So I didn't write down all the words, but you just give your favorite two-plane field, and there should be an over-twisted contact structure which, as a two-plane field, it is homotopic to it. So in other words, we can summarize this theorem by saying that in every homotopy type of two-plane fields, there is a unique over-twisted contact structure. Or in other words, over-twisted contact structures up to isotopy is the same as two-plane fields up to homotopy. So in other words, somehow the classification of over-twisted contact structures is really a homotopy theoretic question. You can imagine that somehow Gromov's H principle is just satisfied for these objects, although I think the proof doesn't use the H principle. And I would like to spend a little time later on addressing the question, how can we understand, how can we have a better grasp on the homotopy classification of two-plane fields? So we'll return to that. It's not a very difficult question. But the lesson we have to learn from it is that if we would like to answer this problem or understand the difficulties in this problem, we have to focus on tight contact structures, and this is what we will do from now on. Of course, there is a question whether tight structures exist at all, and there is another theorem which is usually attributed to Eliashberg and Gromov, that if Y psi is fillable, then it is tight. So fillable means that there is a symplectic four manifold as above which is compatible with it. So if there is sort of a four-dimensional big brother, then Y psi is tight. Of course, it doesn't really answer the question whether such things exist, because I didn't give you any example of a compatible pair. Question? Weakly fillable. So fillable from now on will be always weakly fillable, except for some little remarks sometimes. There is a natural question which you should ask. But if you don't, then I will ask, whether the implication holds in the converse. So if you have a tight structure, is there an X omega which shows its tightness through this theorem? So the question is this. And the answer to this question, I can tell you, it's no. And the first such examples of tight but non-fillable examples were found at Nair and Honda, and later on I hope to give you plenty of such examples. So we'll see such examples. Okay. So before going any further, let me just give you a couple of standard examples, mainly to set up the notation. Okay. So of course the standard example is the Euclidean 3 space and alpha should be dz plus x dy, which is essentially the same contact one form Tobias was using, but for some odd reason, depending on your education, you might write minus y dx, but that should be the same. Or you can take, what else do we have to take? So then psi standard is just the kernel of this one form. It's not very hard to check that in fact the inequality which qualifies a one form to be a contact form is satisfied for this. And an isotopic one can be given by the following form, which is dz plus r d theta, where the way I use coordinates in R3 is we have the z-axis, and on a perpendicular plane we use polar coordinates. And these compactify to S3, so we can use the one-point compactification, and these contact structures actually extend to S3, and this we get the same contact structure as considering the following to complex tangencies in or on S3 sitting in C2. So let me just elaborate a little bit on this sentence. So we have D4, the 4-ball, which we imagine to sit inside C2, and on the boundary we can take the complex tangencies, namely the complex lines which are in the tangent space of the 3-sphere. They will give you a two-plane field distribution, and it turns out to be the same contact structure as this one. And let me give you one more. So we can take on R3 the following psi1, which is just the kernel of what? Of cosine r dz plus r sine r d theta in the same polar coordinates as in this point, and you can directly verify that in fact this contact structure contains an over-twisted disk. Okay, so the first example will be called the standard contact structure on R3. The compactification will be called also the standard contact structure on S3, and this is what we will be mainly concerned about. And there is this fourth example where we just sort of modified the form a little bit, and if you spend a little time with it, you can convince yourself that it is over-twisted. It's a good exercise to find the over-twisted disk, unless you know which one it is. Okay. So these are sort of the first examples. The next topic we should cover is special curves in contact 3 manifolds, and this is what will lead us to the HUN-REN curves. And again, I rely a little bit on your memories from Tobias's lectures. So we say that L in y psi is a Legendre curve, Legendre knot, if L is a knot, so it's an embedding of S1, and the tangent of L1 of L is in psych psi, i.e. if you evaluate the contact 1 form defining psi on the tangents of the knot, then you will get 0. Okay. And you might also remember from Kalman Tamás's talk that there is a nice way to sort of graph or draw pictures for such knots when they happen to be in R3 with the standard contact structure. So if this is a very special and very important special case, so I would like to just go through that very quickly. So if you have a Legendre knot in the standard contact R3, then can take its projection to the YZ plane, YZ projection, and since we know that alpha, the defining 1 form, vanishes on the tangents of L, we can use this equation and the definition of alpha to realize that it determines L since X is just minus dz over dy. So, in knot theory, usually if you have a projection, it doesn't uniquely determines you the knot. It's unclear how high you have to lift it. But if you have a Legendrian knot, then luckily the projection, where you only have the z and the y coordinates, already determines the x through the equation that this particular 1 form should vanish on the tangent of the curve. And this is the formula. In fact, so we have to make a few, probably in fact is too early, we have to make a few observations. So for example, since x is a real number, it cannot be infinity, it means that there are no vertical tangents of such a projection, and also one type of a crossing is not allowed. So in the projection, there are no vertical tangencies, and no crossings of this type. And it's not very hard to see that in fact if you take yourself to these two rules, then any projection can be lifted uniquely to a Legendrian curve. So the lesson is that somehow we can just draw everything on the YZ plane and then everything is determined in the 3 space, which is sort of convenient. And the other fact is that every knot K can be C0 perturbed to be Legendrian in R3. In fact, it is true in any contact 3 manifold, but so the point is that you just have a random knot, a smooth knot, and you can just move it a little bit until it becomes Legendrian. If you drop the C0 requirement that you don't want to perturb it too much, then this is a very easy exercise and I advise you to try to solve it. So if you are allowed to make big moves. You just take a projection and you try to avoid vertical tangencies by substituting them with 2-3 cusps, and try to avoid these kind of crossings by trading them to the allowed crossings. Okay. Legendrian knots come with a framing, a trivialization of their normal bundles, which will be very important for us. So, definition, the framing along L in Yx psi, whenever I write L, I implicitly think that it's a Legendrian knot. So the framing along a Legendrian knot given by the orthogonal to psi is called the contact framing. Now this is a perfect source of confusion because you have to remember what a framing is. A framing is just the trivialization of the normal bundle. In this dimension you can just describe it by one single section of the normal bundle. So in other words, if you have a knot and you draw a nearby knot going very parallel to it and twisting in some number of times, this is what the framing is. And there is the contact framing, but unfortunately in many cases there are other obvious framings. So framing can be induced by a surface containing a knot We saw many examples of that in Cameron's lecture, where somehow the surface, where the knot was lying naturally on some surface, and he computed what the framing induced by the surface is, or if L in the first homology happens to be 0. So the first possibility after the contact framing comes, for example, if you have some kind of a natural fibration and you require the knot lying on some fibers. The second can even happen more frequently, for example, in R3. So what is this other framing? Let me just very quickly define it. So remember, in order to perform surgeries, we had to fix mu and lambda on H1 in H1 boundary y minus k z. And the way you usually fix the meridian is the knot, which is contractible in the neighborhood of the knot. But if the knot is null homologous, then you can specify lambda by requiring that it should be contractible in the complement of the knot. So mu meridian is the circle null homologous in the neighborhood of the knot, and lambda, the longitude or latitude, is the circle null homologous in y minus nu k, if the knot happens to be null homologous. So, for example, when we have a knot which is Legendrian, but it's in R3, then actually we have two specified framings. We have the contact framing, and we have this, what I will call the Ciphered framing. It comes from a Ciphered surface. And it would be nice to have a translation between the two notions, and this is given by the so-called Thurston-Banachine invariant. So the definition TB of L is by definition what's called the Thurston-Banachine invariant. Invariant is equal to the contact framing measured with respect to the Ciphered framing if it exists. So, for example, if the knot is null homologous, then it exists, like in R3, and then you will get a number. The Ciphered framing is a nearby knot going around your knot a couple of times. The contact framing is another knot going around your knot a couple of times, and the question is how many more times it goes around, or less. Luckily, if we draw these knots in R3, then it's not very hard to compute these various framings. And here is a formula. So I will call it a little lemma, which says that so this Thurston-Banachine number of L, so suppose L is in the standard 3 space, then TB of L is nothing but the right of L of the projection minus 1/2 the cusps, the number of cusps. So probably it is time to draw an example of a Legendrian projection. So this is my favorite. Once I went to a lecture of Raoul Bott, and he said that if you want to become a knot theorist, it's good to know how to draw the trefoil. So then I learned how to draw the trefoil. You should do the same. This is the Legendrian trefoil. So we can compute the Thurston-Banachine invariant of that knot by computing the right, which is just the signed double points. There are 3 double points, and they come all with a plus sign, and we have 4 cusps. So the formula tells us that the Thurston-Banachine of the trefoil, of this trefoil, is 1. And there is another related number I would like to define. Yes? Of what? Oh, the signed sum of double points. So what you do is you fix an orientation on the knot, like this, and then you go around, and whenever you come to an intersection, a double point, then either you turn like this, or you have to turn like that. This is positive, and the other one is negative. And you just sum them up. You have to make sure that it doesn't depend on the orientation, but it doesn't. Okay, and there is one more piece of information we need from these knots. So if there is a sigma in y psi such that its boundary is a Legendrian knot, then actually we can compute the following quantity. We can integrate the Euler class of the two-plane field against this sigma. Of course, we usually don't like to integrate second cohomology classes. Remember, psi is a two-plane field, oriented, so it has an Euler class. It's an integral class, and we would like to integrate it on a non-closed surface, right? The surface has boundary. This only makes sense if we trivialize psi along its boundary. But this is why we chose a Legendrian boundary, so its tangents can serve as a trivialization along the boundary. Of course, this to make sense, you have to orient the boundary, or equally you have to orient the surface. So this number, which is called the rotation of the Legendrian knot, will depend on the surface and also on the orientation of the knot. And a little remark, in R3, its standard structure, the rotation number is independent of sigma. Somehow, because we don't really have homologies, this will not depend on sigma, but it will depend on the orientation. But depends on the orientation. And so here is the formula how to actually compute. So in R3 standard, the rotation number of a Legendrian knot can be determined from its knot projection, from this YZ projection, by taking the number of up cusps minus the number of down cusps, where we just fix an orientation, and when you pass a cusp, either you go down or you go up. So for example, this is a down cusp, this is a down cusp, this is an up cusp, and this is an up cusp. And the rule is you just take their difference and you divide it by 2. So in this case, for example, you will get 0. Notice that it might depend on the orientation. In this beautiful example, it does not. But what if I modify the picture a little bit and I consider this Legendrian knot, then I just introduce two new up cusps, and then the number will change. Okay. So I guess I just want to conclude this section by two theorems. The first is a theorem of Banachkin, which says the following, that if L is in the standard R3, then we have an inequality which says that the Thurston-Banachkin plus the absolute value of its rotation number, you see, because we are in R3, it doesn't depend on the surface, is less than or equal to minus the Euler characteristic of any surface sigma with d sigma equals L. So if you spend a little time with it, you realize that as a corollary of this theorem, we can say that R3 of Xi standard is tight. Of course, we have to work a little bit, and you can immediately realize that if there is an over-twisted disk, then its boundary is a Legendrian knot which has 0 Thurston-Banachkin invariance, so this will be 0, but the Euler characteristic is 1, so this side will be -1, and there is just no way the rotation number can turn 0 into -1 if we take absolute value. Of course, this is not the historic way it happened. So first, Banachkin proved this property, and then he used it to distinguish this contact structure from others, and later on, I guess Eliashberg was the one who gave this number, or who gave this definition of tightness. Is that right? More or less. And actually, Eliashberg went further, and he proved the following theorem, that so y psi is tight if and only if for every sigma with Legendrian boundary, the following holds: Tb of L plus the rotation of L, now with respect to sigma, is less than minus the Euler characteristic. If you sort of confront this form of the theorem with the adjunction formula we usually see in four manifold theory, then you'll just see this striking similarity. You have the Euler characteristic of the surface on one side, minus the Euler characteristic, so it is like twice the genus minus something, and on the other side you see two other topological data, and later on I hope to make the connection by saying that this will sort of correspond to the self-intersection of the surface, and this is the evaluation of the canonical class on the surface. And there is a second part of the theorem which I would like to show you. So this was part one, and part two is that if y psi is tight, then for a closed surface sigma in y, the following holds: and I always, yeah, okay. So again, of course, I forgot to say that we have to have an oriented surface inside a contact 3 manifold, and you can take the C1 of the contact structure. It's an oriented two-plane bundle. I denoted the same quantity with E psi before, but we know that the Euler class and the first-order class are the same. So evaluating this, you should get either 0 if sigma was a sphere, or less than or equal to minus the Euler characteristic if sigma is not a sphere. You have to remember the formula of Peter, what he gave today. He said that if you have a spin C structure with a non-trivial Heegaard Floer group, then the same equality holds. And hopefully the parallel features of Heegaard Floer theory and tight contact structures will be more apparent by the end of the week. Maybe not. Okay. So so suppose we have a knot in a three-manifold. And remember, what the first thing which should come to your mind is to do surgery on this three-manifold along this knot, and this is what Cameron was doing for 5 lectures, so we'll try to do part of it. But to do that, you need to specify 2 things, or you need to specify one thing, the simple closed curve which will be contractible after the surgery, for which this can be done in 2 steps. First, you sort of trivialize the neighborhood of the knot, you fix a framing, and then a rational number just tells you what the surgery should be. So if nu k, if a framing is fixed, then pq, which should be a rational number, or the infinity, defines a new three-manifold, which I will denote by y pq over k. Of course, we have to pay attention to this possible source of confusion, what framing we took. The result will heavily depend on the framing, as it will depend on the surgery coefficient p over q. But we have natural framings when the knot is contractible, or not contractible, but zero in homology, or if it is Legendrian in a contact three-manifold. From now on, whenever we see a link or a knot in a contact three-manifold, which is Legendrian, then I will always measure surgery coefficient with respect to the contact framing. This is what always exists for Legendrian knots, and the Ciphered framing either exists or not, depending on whether the knot is zero in homology or not. Okay, let me just remind you, if p over q is infinity, then we just didn't do anything. Right? We just took out something and glue it back in the same way. And you have to notice that it doesn't depend on the chosen framing, as it shouldn't. And another remark, if p over q is integer, then there is a natural cobordism between y and ypq over k. And this was sort of hinted by Peter in his lecture, and I hope to return to this point again. And once again, you have to notice that being an integer doesn't really depend on the chosen framing. So this is sort of a property of the surgery, not the chosen framing to which we sort of measure it to. Okay. Now there is a whole calculus how to handle surgery diagrams. You have a three-manifold given by a surgery where the link is living in S3, and there is a whole calculus which says what diagrams give you the same three-manifold, and I plan to sort of cover parts of it, but maybe I will just give you a small hint what are some important allowable moves, and I will not cover the whole theoretic background. This is what we will need. So, example of 2 diagrams giving the same three-manifold. So, example number A is this. So you have a knot, whatever the knot is, and it is integer framed. And there is another one which just circles it. It's like the boundary of a normal disk, rationally framed, and it's the same as just taking n minus 1 over r surgery on this single knot. So you can just flip it over that. And actually the proof is not very hard. You just do the two surgeries one after the other. First you cut out a little neighborhood of this knot and you glue it back as the framing tells you, and you realize that the new core will be parallel, will be isotopic to this guy. So when you do the second surgery, you just take out the same thing again and glue it back in a different way. So the two moves can be summed up in one. Of course, you have to compute the actual surgery coefficient. So this is what we usually call the slam dunk. I'm completely unaware of the history. I know that there is a history behind that, but I don't know. And there is the other one, which I would like to use, which is called Raphson Twist, which is this. There is a number of strands passing through one unknot. So here it's let me just draw the important points. This first curve can be whatever. The second one should be the unknot. This should be an integer. This can be a rational number. If you just forget and flip the rows, then you get something complete nonsense. Here we have a couple of knots passing through the same unknot, which is P over Q framed. This is the same as introducing an N twist and here instead of P over Q you get P over Q plus NP, and if you have a component Ki with framing Ri, then the same component will have framing Ri prime, which is Ri plus n times the linking number of Ki with this fixed curve K. So the reason of complication is that these various strands might correspond to the same knot. It just goes away and then comes back 5 hours later and it passes, and then it can do it in many times. A special case of, what's it? Oh, I see. This means that it's a magic box. The strands just come in and it turns them n times to the right and spits them out again. So for n equals 2, yeah, well, I told you orientation is sort of important. This should be when you have two strands and n equals 2. You just do two full twists. So you just turn them completely. Let me just write down a special case. If n equals 1, then, if n equals plus or minus 1, then we have the following simplified picture. So here we have plus or minus 1, which is equal to minus plus 1, and that's it. What happens is that this other circle will pick up an infinity framing. Okay, so if you have a plus or minus 1, so P over Q, both are 1 in absolute value, but say this is 1 and this is also 1, so you do a 1 surgery, then with n equals 1, here you will have 0, and this means that you do an infinity surgery along the circle, so you can just forget about it, as far as the 3-manifold goes. Okay, so this is sort of a nice move. The way you should understand it is when we just pull it out, then you just become, the knots become sort of tangled. You just introduce a full twist. Or in other words, when you just take out the neighborhood of the circle and you glue it back, the 3-manifold doesn't change, but somehow it gets sort of tortured and twisted. And the way you see it is that the knots, which were like straight, they become spinning around. Okay, examples. Pardon? This?
No.
This?
No.
Square. Yeah, square. Where is the square? Yeah, sorry. Here is the square. Right. Thank you. So the length space can be given by minus P over Q surgery on the unknot. That's sort of an overall conflict. So some people like to say this is the P over Q surgery, which sort of logically makes sense, except if you use the traditional orientation coming from complex geometry, then this is the best. This is the better thing to take. But I will not go into that. Let's take this convention. And there is an easy exercise. Try to solve that this can be given as an integer surgery on a link. So try to turn this knot into a link where all the surgery coefficients should be integers, and this is a very useful hint to solve that exercise, in fact. And the other example I would like to show is the small ciphered surfaces. So if you just take a zero-framed unknot, then the result will be S1 cross S2, as we all know. What zero surgery means is that we just flip the order of meridian and longitude. And so you just decompose S3 into these two solid tori, and you just take out one and flip the role of meridian and longitude, and you glue it back. What you get is S1 cross S2. This is a ciphered fibered space. By definition, ciphered fibered spaces are unions of circles, so this is a union of S too many circles, but it doesn't have any singular fibers, so we can just introduce singular fibers. And so, by definition, the small ciphered surface, remember, a ciphered fiber three-manifold to be small, it needs to be fibered over S2, and it must have at most 3 singular fibers. So this is, by convention, minus 1 over R1, minus 1 over R2, minus 1 over R3. Don't ask me why to take minus 1 over these guys. This is how it is. I mean, this is what convention dictates. Okay, does this picture make sense? And the zero. Sorry. If it doesn't make sense, there should be a good reason. And, okay, so this is what a small ciphered fibered space is for our purposes. And so there is a natural number we can associate to it, which is just E0 of M, which is just the sum of these Ri's. And here's a little example or an exercise. Show that MR1, R2, R3 is actually the same as Q1, Q2, Q3, E0M with Qi less than minus 1. So although we cannot say anything about the signs here, but if we just torture the picture a little bit using these moves, then you can assume that. And if E0 is non-negative, then M, R1, R2, R3 is the same as 0, Q1, Q2, Q3, and Qi are negative. So we'll use these presentations of these special ciphered fibered space, small ciphered fibered spaces later. It's just an amusing, well, depends on the amusement you like, but say it's an amusing little exercise. Yeah, sorry. Okay. So we have a way to sort of manipulate with diagrams and describe the same 3 manifolds in many different ways, but what can we say about the contact structures? So in other words, can we sort of mimic this surgery procedure in the contact world? And the answer is, Of course we can, otherwise I wouldn't lecture about it, right? So the definition, or let's say contact surgery. So suppose L is a Legendrian knot in a contact-free manifold Yxi. Then what we can do is the following. Then take Y minus the neighborhood of this curve, which is still a contact-free manifold. Now it has a boundary. If you just take the open neighborhood, it will have a boundary. And what you can do is just take this solid torus, what you took out, and glue it back again. So glue back S1 cross D2 to perform a surgery, let's say an R surgery along L. Now the question is whether the contact structure extends. So the schematic picture you have to have in mind is something like that. So you have this Xi everywhere on Y. Then you take L, we delete it, so on the complement there is still the contact structure. And then we glue it back in some way, and the question is whether it extends or not. And without explaining the details how to prove it, here is the theorem. So first of all, as I hopefully convinced you, we are not really interested in over-twisted contact structures. And over-twistedness is a property you can introduce in a small piece of the manifold, right? It just requires the existence of a disk. So we better look for tight extensions, which are at least tight on the new solid torus. It might be over-twisted overall, but it should be tight in the solid torus. So here is a theorem which goes back to the work of Honda and maybe Giroux. Giroux is like you put it everywhere, right? Saying that if we perform plus or minus 1 surgery, remember we measure the surgery coefficient with respect to the contact framing, then psi from Y minus nu L extends uniquely up to isotopy to the result of plus minus 1 surgery along L such that it is tight on the new solid torus. So by this I mean that when you do a surgery, you just take out the neighborhood of the knot, and this is the solid torus you will glue back. This is what I call the new solid torus. The extension should be tight over that solid torus. And the theorem says that there is actually a unique way to do that. Okay, so let me just make a few comments.
Next board instead of that board?
Sure. You know, for a while you are following which board is first, second, and then you just confuse and you stick to one board. And actually sometimes you just stick to the corner and okay, so a few comments. So we need L to be Legendrian because it has a canonical neighborhood or standard neighborhood. This is how we know what the contact structure on the boundary of this neighborhood is, and then we can ask what is how many extensions we have. So to extend, need classification of tight structures on S1 cross D2, and this is actually what Honda was doing, so we use this classification. And so using this classification, we see that any R surgery can be done if R is not equal to 0. So we always have a tight extension. Again, it will be tight only on the new solid torus. We don't know whether it will be tight overall. R could be anything. Here I just restricted myself to plus or minus 1 because this is what we will use later. R can be anything unless it is 0, in which case the R surgery, contact R surgery is undefined. But for general R, the result will be not unique. So there is always such an extension, but it is unique if R is of the form 1 over k, where k is an integer. So and then somehow you can see why we stick to plus or minus 1. So the diagram determines the surgery manifold if the coefficients are of the type 1 over k, but we have a 4-dimensional cobordism if R is an integer, and the two requirements meet only if R is in fact plus or minus 1. And as you will see, I'm really mainly concerned about these 4-dimensional objects, the cobordisms. And so here's the concluding theorem I would like to announce, and next time I would like to prove. And this is a theorem of Ding and Geiges. And this very much echoes this theorem of Licorice and Wallace we just heard in John's lecture. And this says the following. If y psi is given for whatever, given contact 3 manifold, then there is a Legendrian link in S3, in the standard S3 sphere. There is a Legendrian link having many components, and the components are classified to plus or minus, or red and white, in 2 different groups, such that plus 1 surgery, contact plus 1 surgery, on L plus and contact minus 1 surgery on L minus gives y psi. So this theorem tells us that when we are talking about contact 3 manifolds, in fact we can restrict our attention to Legendrian knots in S3, and they have to come with an additional data. Some are in the L plus group, and the other ones are in the L minus. And so let me just spend one more sentence about this problem, what I posed at the beginning of the lecture. So we would like to classify contact, okay, I don't touch this board. We would like to classify tight contact structures on 3 manifolds, and in order to do that, we sort of need 4 tools, and I listed them. So to classify, we need to have examples. And this is provided by contact surgery, for example. So this is one way of doing examples. Legendrian knots in the standard S3 and doing contact surgery. Then we have to prove tightness. This is sort of a harder job, and there are existing methods like state traversal method, which is purely 3-dimensional. We will use the contact Augeat-Szabó invariant, which I will introduce in lecture 3, and we will see how Heegaard Floer theory comes into the business. And we will need a way to distinguish. There are many methods for that. I will just run through the homotopy theoretic. So how do you distinguish contact structures? By just distinguishing their homotopy type, or Augeat-Szabó invariants, and some other means. And finally, you have to show that you have many examples. You know that they are all tight and they are all distinct, and you have to show that there are no more examples. And this is, so no more. And this is usually provided by convex surface theory. And hopefully we'll hear about that later this week as well. I guess this is all what I wanted to say today, and next time we will just get back to the theorem, to the proof of this theorem, and I will amuse you with a couple of, this manipulation of links, if you don't mind. If you do mind, well, then I don't know. Okay.